Now in this question, again we have to use Lenz law to determine the direction of the induced current in the situations described by these two figures. So in this figure A, here it is given that we have an irregular shape loop and we have to turn it into a circular shape. So how we are turning it into a circular shape? By stretching it out, and it is going to take the shape, this circular shape. So when we stretch it and try to have the circular loop, this means that the already existing field that is perpendicular to the screen and away from you will increase the flux, or by this process you can say the flux will increase. So the direction of induced current will be such that it will create the field in such a way that it will not let the flux to increase. So for this situation we need magnetic field perpendicular to the screen towards us. So in order to produce such kind of magnetic field perpendicular to the screen and towards us, so the direction of the induced current must be anti-clockwise. So the direction of induced current must be written as A, D, C, B, A. Right? Now, in this case B, here we have a circular loop and it is deformed into a narrow straight wire. So, if you look carefully, here the magnetic field is towards us, and when we are trying to squeeze it to this tube shape, so basically we are doing what? We are trying to decrease the magnetic flux. So when we are trying to decrease the magnetic flux, so the direction of induced current will be such that it will not let the flux to decrease. So it will arrange itself, the induced current will arrange itself in such a way that it will support the already existing direction of magnetic field or already existing magnetic field. So in order to get the magnetic field in the same direction, the direction of the magnetic field must be like that. So it must be anti-clockwise again. So the direction of induced current is again, that would be A, D, C, B, A, right? Now in this question, part A, we are given with two loops. One loop is a rectangular loop and another loop is a circular loop. And both of the loops are moving out of a uniform magnetic field to a field-free region with a constant velocity. So this is a rectangular loop and this is a circular loop, and they are coming out of the magnetic field. In which loop do you expect the induced EMF to be constant during the passage out of the electric passage out of the field region? The field is normal to the loops. Now this is very interesting. So for this we have to focus on the formula phi equals to BA, assuming cos 0 degree is 1. Now to induce EMF, we have to look for the rate of change of magnetic flux. I am taking the modulus. So here B is constant, but what is changing? dA by dt. And if you want a constant EMF, so this can only happen when the rate of change of area is constant. Now when you pull the loop out, so there is a, you can say, for every second, the amount of area, this small amount of area that is coming out of the magnetic field is basically constant. So for this rectangular loop, definitely the EMF that will get induced is constant. But if you look at this circular region, now see, this is a stage when the loop is coming out. So if we look out at the area that is coming out per second, so that is not uniform. See, so there is a difference in area. Every time as you pull this loop outside the magnetic field, the area coming out per second is not constant, it is a variable. So only for this rectangular loop that is being pulled with a constant velocity, here the area that is coming out per second is constant, but in the case of circular loop the area that is coming out per second is not constant. So only for this rectangular loop the EMF induced will be constant, right? Now this B part, that is very interesting part. So in this B part we have to predict the polarity of the capacitor in the situation described. So for convenience we are just considering this magnet. Okay, now as soon as you move this magnet towards this coil, okay, and when you move this magnet towards the coil, so what you expect? You expect that the current that should be induced in such a way that this induced current will create a field that will not let the magnetic field to this magnet to come closer as per the Lenz law. Okay, and we have to predict the polarity of these plates of the capacitor. So whether A is negative or positive or B is positive or negative. Okay, so you can just pause the video and predict that what should be the polarity of A and what should be the polarity of B. Right? Now, in order to tell the polarity, you have to be very careful about the direction of current inside the battery. Yes, inside the battery. Now look at this situation. Now this is a battery having EMF E and this is resistance R. Now if you are asked that what is the direction of current, so your general answer is that the direction of current is from the higher potential terminal to the lower potential terminal. But this is partially true, because the direction of current that you are saying is from the higher potential terminal to the lower potential terminal is outside the battery. But what is the direction of current inside the battery? So inside the battery having EMF E, the direction of induced current, the direction of current is from the lower potential terminal to the higher potential terminal. And this is the key here in the question. Now, as the current we are expecting to be in this direction as per the Lenz law, right? So the EMF that will get induced in the loop, now this loop in itself is acting like a source of EMF, and in the source of EMF the direction of current is from the lower potential terminal to higher potential terminal. So the polarity B, polarity of plate B will be negative and the polarity of plate A will be positive, right?